Hi folks, in this tutorial we'll be trying to determine the rate orders of the various reactants in a chemical reaction. Scientists have determined that one of the factors that affects the rate at which a reaction proceeds is that of the concentration of the reactants. However, the multi-million-dollar question is, does a change in the concentration of every reactant in the reactant system affects the rate at which the reaction happens the same way? The only way of knowing that is to carry out experiments using various concentrations of the reactants that are involved in that chemical reaction. On the board is written the chemical equation that represents the reaction between an aqueous solution of sodium thiosulphate and hydrochloric acid. And as you can see, that the products that are formed are solution of sodium chloride, water, gaseous sulfur dioxide, and a yellow precipitate of sulfur. We will use the rate at which the sulfur is being produced to monitor the rate of this reaction. How can that be done? What we'll do is this. This is an X that's written on this paper here. We'll take a beaker and put it over this X and let this rest on the table. In this beaker, we will add the two reactants. The moment we add these two reactants together, we start our stop clock. As the sulfur is being formed, it obscures this X from our vision. So you can see right now, this X is very visible to us. As the sulfur is being formed, gradually, when you watch there, the X disappears from vision. At that time, we stop the stop clock and we look at the time from the beginning of the reaction to the end when the X disappears, and we record that time. We start that experiment by using these concentrations of hydrochloric acid and sodium thiosulphate, 0.2 mole per liter, 0.2 mole per liter, and we take 25 milliliters of each and pour them into the beaker. After that is done, we'll do a new experiment. We'll do experiment 2. In that case, we'll change the concentration of the sodium thiosulphate, but we'll keep that the same because you can't change two variables at the same time. We change this one here by reducing its concentration to that. Finally, we will retain the original concentration of the sodium thiosulphate, but reduce the concentration of the hydrochloric acid to half and see if there's a difference in the time that it takes for X to disappear. Okay, in this first experiment, we will be mixing 25 milliliters of 0.2 mole per liter HCl with 25 milliliters of 0.2 mole per liter sodium thiosulphate. So we'll quickly mix these, start the stop clock. So here we go. Give it a little swirl. And then we watch for the time that it takes for the X to disappear. That's it. So one of the things that we will not make a big fuss about is the time that it takes for this X to disappear, because you can see it is highly subjective. We could not have been coordinating with this stop clock and the time that it takes for the X to disappear. So you will make a big fuss if you have a few seconds difference in these trials. Okay, we're just looking for a pattern. So we'll hold this time for now. In the second experiment, we'll be retaining the concentration of the hydrochloric acid while we're reducing the concentration of the sodium thiosulphate to half of what it was before. What do you think? Make a hypothesis as to what time you think it will take for that X to disappear. we're reducing the concentration by half. Do you think it's going to take the same time, more time, or less time than this one here? Okay? All right, that's what we're going to do now. In experiment number 2, we are retaining the concentration of the hydrochloric acid, which is 0.2 mole per liter, but we have reduced the concentration of the sodium thiosulphate to 0.1 mole per liter. That was achieved by taking 12.5 milliliters of the sodium thiosulphate and then add 12.5 milliliters of water to that to make 25 milliliters. Okay, so now we start the second trial. Start. Make a hypothesis as to how long it will take. Here it goes. Stop. Around 36 seconds. So you can see that in the second experiment, it took twice the amount of time for the X to disappear. Now in the third experiment, look what we're doing. We are retaining the concentration of the sodium thiosulphate as it was in experiment 1, but we are decreasing the concentration of the hydrochloric acid. Now, in this case, we reduce the concentration by half, and we got that time for the X to disappear. What do you think will happen now that we're reducing the concentration of the hydrochloric acid by half, and we are having that concentration of the sodium thiosulphate? Make your hypothesis. If you follow the trend, you might want to say that it should take that time there. So to verify that, we'll do the third experiment. So here we go, the third experiment. Stop it. Okay. Let's see how long it takes for the X to disappear. Keep your hand there. 16 to 17 seconds. All right. I think you should have gone to about 18 seconds. Okay. All right. We're not going to make a big fuss if we are out by a few seconds. We're just trying to establish certain patterns, right? So we'll call this 18 seconds. This will be 36. And you're expecting that because we reduce the concentration of that by half, and you got 36 seconds, the same thing would have happened here. But that's not the case. It is exactly what the first one was. See, that is why you just cannot follow the pattern or the trend, because that one was reduced by half, and I give a time of that this one would also be the same. And this is what is related to what we call the rate orders of the reaction. We have to carry out experiments to establish rate orders. One point to note is this. In your textbook, you're going to see another column that's called rate. We have just gotten the times here, okay? But we have not calculated the rate for each of these experiments. So we want to make one assumption here, and I hope that this assumption is perfect. For that X to have disappeared from our view, a certain amount of sulfur must have been precipitated. And since the volumes were the same, then the concentration of the sulfur that was produced in every case must have been the same. We do not have the technology to measure the concentration of that sulfur, but we can assign an arbitrary value to that. We will say that there was X moles per liter. X moles per liter in every case. So we can now go ahead and find the rate by taking X moles per liter in every case and divide it by the time in every specific instance. Okay? So why don't you do that for us? Take 1x and divided by 18, then 16 and 18, and we put the rates there. Do that as a practice for me. And then we see, I'll do it too, then we see if your answer corresponds with mine. These are the values that I got. 5.56 times 10 to the negative 2 x moles per liter
per second.
2.78 times 10 to the negative x moles per liter
per second.
And this one here, same as that. So when we want to find the rate orders for the reactants for a particular reaction, this is what we do. We first of all look at the reactants and express the hypothetical rate law equation. We're going to say that rate is equal to K, which is called the rate constant, times the concentration of the thiosulphate raised to some exponent. We use any letter of the alphabet to represent the exponent. U, A, B, C, X, Y, and Z, times the concentration of hydrochloric acid raised to an exponent Y. Now, to know what the values of X and Y are, we have to do some calculations. We look at the change in rate when one of the reactants is changed. We can say that we started with 0.1 mole per liter of sodium thiosulphate, and we doubled its concentration. So at this concentration, that was the rate. When we double the concentration, look what happens to the rate. The rate is doubled. So this is the deal. If when you're doing these experiments, if the concentration of one of the reactant is doubled, and the rate is also doubled, we will say that it has a rate order of 1. So now this X is now replaced by a 1. Now we want to compare the rate of the reaction when the concentration of the hydrochloric acid was changed. So we can look at it from this perspective now. Let's suppose that we started with 0.1 mole per liter, and that was the rate. Now we can say that in this case though, we have doubled its concentration, and look what the rate is. The rate did not change. So this is the deal. If the concentration of one of the reactants is changed, and there is no change in the rate of the reaction, we will say that that reactant has a rate order of 0. In this case now, we will put a 0 here. So the Y becomes 0. But when you're writing what is called the rate law equation for this reaction, anytime something has a rate order of 0, it is not included in the rate law equation. So this is the final rate law equation for the reaction between sodium thiosulfate and hydrochloric acid. Only a change in sodium thiosulfate produces a change in the rate of the reaction, and it does it in the order of 1. This is a rate constant. And the other video that I've done discusses how the rate constant is calculated. So I hope that was useful. You do another activity to enhance your understanding of rate orders. Thanks. In this other activity, we will try to determine the rate orders of the following reactants: iodate ions, iodide ions, and hydrogen ions. These react when combined together to give water and iodine. Of course, this is in the form of potassium iodate, that is in the form of potassium iodide, and that is from sulfuric acid. We'll monitor the rate of this reaction by looking at the rate at which iodine is formed. When iodine is formed in solution, it is not very visible. However, in the presence of starch, you see a very distinct blue-black color. And that is what we will use to identify the iodine in this case. I just want to show you a little demo of how iodine changes color in the presence of starch solution. In the presence of an oxidizing agent, iodide ions are changed to iodine molecules. And that is what is going to happen inside here, this reaction. The iodide ion here, in the presence of iodate and hydrogen ions, we will change to iodine. I just want to show you how that happens. So this is a solution of potassium iodide. Yes, iodide ions right there. In the presence of an oxidizer such as hydrogen peroxide, this is what happens. You can see a change in the color of the solution. It goes slightly, well, that color I don't know how to describe it, it's like the yellow or something like that. However, in the presence of starch solution, this is what happens. See? A dark blue solution is formed. So when we react iodate ions, iodide ions, and hydrogen ions together, iodine will be produced, but in one of those solutions, we have added some starch to it, such that when the iodine is formed, we'll end up with that color. As we did in the previous activity, we were having different concentrations of iodate, iodide, and hydrogen ions. In the first experiment, we were having 0.2 mole per liter for each of these. We mixed these together, we started the stop clock, and the moment that blue-black color appears, we stop it, and that will register for us the time. And that will help us to calculate the rate at which the iodine was being formed for that reaction. In the second reaction, we will retain the concentration of hydrogen ions and iodide ions, but we'll change the concentration of the iodate ion from 0.2 to 0.10. And we repeat the same thing, mix them together, and we look for the appearance of that blue-black color. And in this one here, we retain the concentrations of the hydrogen ions and the iodate ions, but we reduce this to half of that. And repeat the same experiment, mix them together, look at the time for which it takes for that blue-black color to appear. Finally, we'll only change this one here, but we will retain these. In the other video that I've done, I'll stress the importance of initial concentration. Watch that video again, and you'll see why we're using that word. And we're also looking at the time for the initial production of iodine. So that is what we're going to do now. We're going to carry out these experiments. This reaction follows a similar trend as what happened between sodium thiosulphate and hydrochloric acid. Recall that the moment we mixed the sodium thiosulphate solution with hydrochloric acid, a precipitate of sulfur started to form. In this case, the same thing is going to happen with iodine. The moment you mix these together, iodine begins to form. So to measure the rate at which that iodine is formed, we first of all mix the three reagents together on the stop clock. And what we have done is something similar to what we did for the reaction between thiosulfate and hydrochloric acid. Only in this case, we put a white piece of paper beneath the beaker in which all these things are mixed. Then we look at the time for that piece of white paper to disappear, and we record that time. We'll do the same thing for the other experiments when we change the concentrations of those, okay? So we'll start the experiment up by putting in one reagent, no problem. Now we'll mix the other two together, and we register the time. I have a timekeeper here. So here we go, speed. Give it a little swirl like that. That's it. 30 seconds. So in this second experiment, we'll change the concentration of the iodate ions from 0.2 mole per liter to 0.1 mole per liter, and we'll retain the same concentrations for the iodide and sulfuric acid. So we start a stop clock now, and see how long it takes for that white piece of paper to disappear. Ready? Go. Give it a little swirl. Okay. What time you have there? 1 minute and 1 minute is like about 62 seconds. In this third experiment, we are reducing the concentration of the iodide ion from 0.2 mole per liter to 0.1 mole per liter, and we have retained the initial concentrations of the hydrogen ions and the iodate ions. So put one aside there. So it's on the stop clock, and we look at the time for that thing to disappear. Okay, here we go. Sorry, we're a few seconds off there. Okay, no problem. Okay. Give it a little bit of swirl if we didn't do that. From my vantage point, it's about to clear up, it's about to disappear. Give it a few seconds more. I would say it's about time now that it goes, okay? Somewhat subjective. All right, so that's the third experiment. 65 seconds. In this final experiment, we have reduced the concentration of the acid from 0.2 to 0.1 mole per liter, and the two others have been retained at 0.2 mole per liter. So you add one. Now, on the stop clock, please. There we go. Give it a nice little mix. Look at the time it takes for the white piece of paper there to disappear. Still very visible. The swirl, we didn't do that. Look like it's about to disappear now, so we'll use that time now, okay? All right, stop the clock. What do you have there? 2 minutes, 13 seconds. So 130 seconds. We have established some patterns, right? This is about 130 seconds, okay? This one was 65, that one was 65, and this one is about 32. So why don't we make that 32 seconds, okay? All right. Now, we can now try to find out what is the rate of the reaction. Remember the last time we made an assumption? In the case of sodium thiosulphate reaction with hydrochloric acid, we said it must have taken the same amount of sulfur to obscure the external vision. In this case, we're making the same point, that it must have taken the same amount of iodine to obscure that white piece of paper from vision. So because we're using the same volume, the concentration must have been the same in every case. So we let that be X moles per liter. Now to find the rate for every reaction, we take X moles per liter and divide it by each of these time here. So why don't you do that as an exercise? These are the rates that I have calculated. I made it in such a way that easy for you to see the relationships. Now, let us try to decipher what are the rate orders for each of these reactants. Now, what we're going to do is this. We can look at this from this perspective, you see. We can say, look, we started with that concentration of iodate ion, and we increase it to 0.2. We double it. You see what happens? The rate has doubled. It changed from 16 times 10 to negative 3 to 31.3. So you can see there is a doubling of the rate. Therefore, we can say that the rate order for iodate is 1. So X becomes 1 here. Let's check it out for iodide ions. This is iodide ion here. This is what it was at that concentration. When we double it to that, look what happens. The rate has doubled. So we can say for iodide ions, the rate order is 1. But let's look at it for hydrogen. When we had that concentration, that was the rate. Okay? When we double the concentration, look, nearly 4 times, the rate quadruples. I mean, of course, we're not very accurate here, okay? We don't have the technology to these things with precision, but we can see a trend. As you double the concentration of the hydrogen ions, the rate becomes 4 times more. And in such a case, we say that it has a rate order of 2. So this will be the rate law equation for this reaction. An overall rate order for the entire reaction will be equal to sum of these exponents there and a 4-order reaction. I hope that was useful to you. In the other video that I've done, I've explained how the rate orders can be calculated in a more formal way. I hope that was useful to you. Please share this video with your friends, and please don't forget to subscribe. Our next video deals with creating reaction mechanisms for chemical reactions. See you.